too. I hope you guys are having a great day. I just want to let you know I just got home. It's really late from a performance, and I'm making a video for you because I love you. Okay, anyways. 5, 4, 2. This is the second day of graphing rational functions, not using transformations. So, we have 3 definitions. I didn't write the SWABAT down just because the SWABAT is graphing rational functions without transformations. It's the same as the title of the lesson. Anyways, so a blank is a function whose graph doesn't have blank. Okay, that doesn't really give you a whole lot of information, but basically there's a couple different types of graphs that we're going to be talking about today. One is a continuous function, and a continuous function is one essentially that you can put your pen down and graph the entire function without lifting your pen up and then replacing it. So it doesn't have holes or asymptotes or jumps or discontinuities. And guess what? A discontinuous function is a function whose graph has at least one of those things, or basically cannot be graphed without picking your pen up. Okay, so let's sketch some of those. So number 1, a continuous function. I'm going to put my pen down and then sketch a graph. Woo! Without picking my pen up. Okay, I'll pick up my pen to draw the arrow on the other side, but I could have done that without picking up my pen. Anyways, okay, that is a continuous function. A discontinuous function might look like this, where all of a sudden it jumps to another point and then keeps going, or it has an asymptote maybe and like looks like that and then looks like that. But if you notice, I had to pick up my pen. Actually, you probably couldn't see that because you can't see my pen. Ah. But you can't draw it without picking up your pen, unless you're magic at all. Okay, lastly is a hyperbola, which the parent function hyperbola is f of x equals 1 over x, right? And we know what that looks like. Looks something like that. So any transformation really of that is a hyperbola. Okay, when graphing rational functions, the first thing you always want to do is factor both the numerator and denominator. Okay, please factor it first. Don't cancel anything out yet, but factor first so that eventually you can cancel stuff out. Okay, so all of the following, so I just graphed a random rational function for you. And these are the main things that you're going to need. So number 1, you're going to have to be able to find holes in the graph. So that would be A, and that's like the little hole that I graphed over here. Vertical asymptotes, so obviously you know what an asymptote is, but vertical would be like this asymptote and that asymptote. Okay, so labeling those. Horizontal asymptotes, right? That would be your horizontal asymptote. Y-intercepts, that's also important, so make sure you're labeling your y-intercepts. That would be D. Here's a B and a B and a C and a D. Real zeros or your x-intercepts. Right? So that's going to be there and there and there in this case. And so your x-intercepts, that's E. Okay, and then lastly is be able to tell me what your domain and range are. So we're going to go over that as we go along. So let's do an example. All right, so here's our first example. Y equals x minus 1 times x plus 2 times 2x plus 1 over x minus 1 times x plus 4. Okay, so this is already in factored form, so you don't have to do any factoring yet. But I just want to show you the rest of it. So step number 1 is finding the wholes. So remember, we always have problems when the denominator is 0. So we know for a fact we're going to have a problem when x equals 1 and x equals -4, right? Because that's what makes the denominator 0. And we don't like zeros in the denominator. So we need to figure out what those problems look like on the graph. So when you start out and you look and you factor everything and you say, oh, hey, look at that. X minus 1's canceled. That's exciting. And then the x minus 1's are gone magically. But they're actually not, because in the first function, x minus 1 is a problem because it's in the denominator. It's not a huge problem. It's not like an asymptote problem because it cancels, but it's like a tiny minuscule problem on the graph, which is why it's a hole instead of like a big asymptote or something. Now, this also begs the question, what is the y value when x is equal to 1? Because it's a hole, so it's like cut out of the graph, but it still has to have a location. And so the best way to do that is just to take the function after you cross out your factors. And then, like as you see here, I crossed out the x minus 1 and x minus 1, so I'm left with x plus 2 times 2x plus 1 all over x plus 4. So that's like my new function. And if I want to figure out what the y value is, I plug x equals 1 into that function. So I would plug in 1 anywhere I saw an x, and I have 1 plus 2 times 2 times 1 plus 1, right, all over 1 plus 4. So that's 3 times 3 is 9 over 5. So the actual whole is 1/9. Okay, next is the vertical asymptotes. So this goes back to when is the denominator 0? When do we have problems? And if you remember, we decided that we have a problem at x equals 1 and x equals -4. Now we already figured out that x equals 1 is just a hole. And so x equals -4, that one didn't cancel out. And so that one is a big problem, which means that one's an asymptote, and that's a vertical asymptote. So basically, after you cancel everything out, whatever's left in the denominator becomes a vertical asymptote. So in this case, x equals -4 is your vertical asymptote. Okay, next are the horizontal asymptotes. And there are 3 different scenarios for the horizontal asymptotes. One, the degree of the numerator is bigger than the degree of the denominator. Second is the degree of the numerator is smaller than the denominator. And then last, if the degree of the numerator is equal to the degree of the denominator. Okay, in the first case, if the degree of the numerator is bigger than the degree of the denominator, you don't have a horizontal asymptote at all. Now, if the degree of the numerator is smaller than the degree of the denominator, then the x-axis is the horizontal asymptote. And lastly, if the degree of the numerator is the same as the degree of the denominator, then really, when in standard form, the ratio of the leading coefficients, old vocab, look it up if you don't remember, the ratio of the coefficients is the horizontal asymptote. All right, so let's look at our example. We have x plus 2 times 2x plus 1 over x plus 4. Okay, and so we want to look at the degree of the numerator and the degree of the denominator. So this is easiest to see when it's in standard form. Maybe eventually you'll get used to seeing it in factored form as well, but I'm actually going to FOIL everything out so you can see this happening. So if you take a look, if I FOIL everything out, my function becomes 2x squared plus 5x plus 2 over x plus 4. This is, again, after everything's canceled out in the beginning. Once you find the holes, then you find everything else. That's why holes is the first thing to find. Anyways, So you look at the degree of the numerator, and for this one, the degree of the numerator is 2. The degree of the denominator is 1. Okay, so that means we are in the first scenario. The degree of the numerator is greater than the degree of the denominator, which means then we have no horizontal asymptote. All right, next is the y-intercept. Y-intercept is the same as it's always been. Set x equal to 0 to find when the function crosses the y-axis. So let's take our function after everything's been canceled, all of the wholes are canceled out, and we just set x equal to 0. So we have 0 plus 2 times 2 times 0 plus 1, which is just 1, 0 plus 1, over 0 plus 4. So 2 over 4, which is 1/2. My y-intercept for this function is 1/2. Next are your x-intercepts, your real zeros, where the function crosses the x-axis. And that's the same thing that it's always been. You set y equal to 0 and solve for x. So in this case, we have 0 equals x plus 2 times 2x plus 1 all over x plus 4. And to solve for x, we can multiply both sides by x plus 4, right? And then we get 0 times x plus 4 is just 0. We get 0 equals x plus 2 and 2x plus 1, which is equal to 0 whenever x is negative 2 and x is negative 1/2. So those are my two x-intercepts. Okay, the last two things that you're going to need are to pick a bunch of points, and until you get used to graphing these types of functions, I'd recommend plotting a decent amount of points. And then eventually we'll find the domain and range, but I wouldn't do that until we graph it. I think it makes more sense to do it when we graph. So let's put all of these things together. I'm actually just going to copy and paste all of our answers from this function onto the next page, just so that we have them as a... All right, let's first graph the whole. So the whole is at 1/9, which is really close to 1, 2, the point 1, 2. Then we plug in our vertical asymptote, which is x equals negative 1/4. We do not have a horizontal asymptote, so you don't need to draw that in. Y-intercept is at 0, 1/2. X-intercepts are negative 2 and negative 1/2. All right, next is kind of connecting the dots and making sure that you have everything that you need. But you know that the function is going to go through both negative 2, negative 1/2, and the y-intercept and stuff. And it's not going to go back through the x-axis. So it has to look something like this. So the only thing is now we need to figure out what happens on the left side of the asymptote because we have no information there. So you're going to have to pick some x values on the left side. So perhaps -5 might be a good idea. -6 might be a good idea. -7 might be a good idea. Any of those points will work. So let's plug them in, and you can plug them in to the function after you've canceled out the x minus 1s. Alright, so when x equals -5, you have f of x is what we want to figure out. So we just plug in -5 for x and figure out what y would be. So as you can see, when I plug in -5, I get -27 for my y value. So my first point on the left side of the asymptote is -5, -27. Next, when x equals -6, y is -22. So I just found a few more points, -7 and -21.6-ish, -4.5 and -40. So let's plot those points on the graph. Oh wait, our graph only goes to -10. Okay, so way down here somewhere, way down here, we have the function happening, and basically what happens is it's gonna look something like that. Way far down. And that would be your graph. And here are your domain and range.